Have you ever stopped to wonder how a massive website can handle millions of users all at once without completely crashing? Well, the answer lies with a true unsung hero of the internet, the load balancer. Honestly, it's the reason our digital world is so fast, so reliable, and can handle just about anything we decide to throw at it.
I mean, just think about something like Black Friday. You've got millions of people all hitting the same website at the exact same moment. How does it not just, explode? The secret sauce is the load balancer, and today we're going to break down exactly how this critical piece of tech actually works.
All right, so to really get the solution, we first have to understand the problem. So let's picture this. Our super popular website is running on just one single lonely server.
And this slide right here shows the core issue. On the left, that one server is basically a ticking time bomb. It's what we call a single point of failure. If that server goes down, the whole website goes down with it. Game over. But on the right, we've got a multi-server setup, which lets us do something called horizontal scaling. This gives us way more reliability and performance, but it also creates a new challenge. How do we manage all that traffic going to all those different servers? Because when that huge flood of traffic comes rushing in, that one server just gets completely swamped. It can't possibly handle all the requests. And the result for you and me? An error page, that spinning wheel of doom, and a whole bunch of really frustrated users. It's just not a system that can grow. So, how do we fix this overload mess and smartly manage the traffic across our whole group of servers? Well, the solution is actually pretty elegant. We hire a traffic cop.
And that's pretty much exactly what a load balancer is. It can be a physical piece of hardware, but these days it's way more common for it to just be a piece of software. It sits right out in front of all your servers, and it acts like a director, seeing all the incoming requests and deciding in a split second which server is in the best shape to handle each one.
This diagram shows the new setup perfectly. See, your request doesn't go straight to a server anymore. Nope. Instead, it hits the load balancer first. The load balancer then looks at its pool of available servers, we'll call them A, B, and C, and forwards your request to one of them. And for you, the user, this is all happening completely invisibly in the background. So the goals here are really simple, but they're incredibly powerful. We're preventing any one server from getting overloaded and becoming a bottleneck. We're making it possible to add or remove servers on the fly so we can scale. And most important of all, we're making sure the application is always available. But wait, how does it decide where to send everything? It's not just random. The load balancer uses a set of rules or algorithms to make these smart decisions. Let's take a look at 3 of the most common ones. First up is good old round robin. This is the simplest method you can imagine. It just goes down the line, taking turns. First request goes to server A, the second to B, the third to C, and then the next one just loops right back around to A again. It's super simple and predictable, but the downside is that it assumes every server is identical and every request takes the same amount of work, which isn't always true. Okay, next, we have a much smarter approach, the least connections algorithm. With this one, the load balancer is actually keeping track of how many active connections each server is handling at any given moment. So, in this example, server B is the least busy. It only has 2 connections. So guess what? The next incoming request goes straight to it. This makes the workload way more balanced, especially if some requests take a lot longer than others. The only trade-off is, it takes a little more brain power for the load balancer to track those connections. And finally, we have a really critical concept called session persistence, which is often done using an algorithm called IP hash. Now, why is this so important? Well, imagine you're on that shopping site, and you've added a few items to your cart. That information is stored on one specific server. Let's say it's server A. You definitely don't want your next click to send you over to server B, because server B would have no idea what's in your cart. So IP hash uses your IP address to create a unique key, making sure you always get stuck to the same server during your visit. It preserves all that important session info. But beyond just spreading out the traffic, maybe the most important job a load balancer has is to make sure your application never goes down. This is called high availability, and it is an absolute game changer. So how does it do this? With something called health checks. Think of the load balancer as constantly tapping each of its servers on the shoulder and asking a simple question. Hey, you good? You still up and running? If it gets a healthy response back, it keeps that server in the active rotation. But what happens if a server has a problem? Maybe it crashes or just becomes unresponsive. Well, that health check is going to fail. The load balancer immediately knows that something is very wrong with that specific server. And this is where the magic happens. It's called automatic failover. The load balancer instantly yanks that unhealthy server out of the pool and redirects all the new traffic to the other healthy servers, A and C. This means there's no downtime, no error pages for the user. The whole experience is completely seamless. This is how you eliminate that single point of failure we were so worried about before. So now that you know what they do, you're going to realize that load balancers are literally everywhere. They're a fundamental building block of almost every large-scale system on the internet today.
Seriously, you'll find them at the heart of so much modern tech. Cloud providers like Google Cloud use them to manage traffic for their millions of services. Platforms like Kubernetes absolutely rely on them to route requests to different containers. And CDNs, or content delivery networks, use them to send you to the closest and fastest server. They're basically essential for any modern microservice architecture.
And get this, load balancers also work hand in hand with another super important cloud concept, auto-scaling. When the load balancer sees that all of its servers are starting to get busy, it can actually trigger the system to automatically spin up brand new servers to handle that extra load. Then, when the traffic dies down, it can tell the system to shut them off to save money. It's just a beautifully dynamic and efficient system.
Now, it's also really important that we're clear on what a load balancer isn't. Yeah, it's a powerful tool, but it's not some magic wand that just solves every single problem with your system.
This table breaks it down really nicely. Look, a load balancer is amazing at distributing work efficiently, but it doesn't magically make your individual servers more powerful. It lets well-written applications scale beautifully, but it can't fix the bugs in poorly written code. And it works alongside other technologies like caching to boost performance, but it is definitely not a replacement for them.
So let's just end with this thought, because on today's web, this statement is the absolute truth. It doesn't matter if you're serving 10 users or 10 million. The ideas of distributing your workload and ensuring high availability, well, that's what separates a professional, resilient system from one that's just waiting to fall over.